This is Concept E classes, and today we'll deal with part 2 of chapter 4 in class 9 science, structure of an atom. So in this video we'll discuss the rest of the topics. We'll see how electrons are distributed in different orbits. We'll study about valency, about atomic number and mass number, and finally we'll deal with isotopes and isobars. So before we enter into part 2, let's take a quick revision of what all we have studied in part 1. So in the previous chapters, all we studied that atoms are the fundamental building blocks of matter, and even Dalton proposed as atoms are indivisible. But in part 1, we saw that atoms are further divided into 3 subatomic particles: protons, neutrons and electrons. We also saw how J.J. Thomson and E. Goldstein discovered electron and protons respectively. J.J. Chadwick, he discovered neutron. And we studied the charged particles in matter, that is, proton is positive in charge, electron is negative in charge, and neutron have no charge. So when people understood that the atoms can be further divided into protons, electrons and neutrons, many scientists started proposing various atomic models to describe the structure of an atom, and J.J. Thomson was the first guy who proposed this atomic model. He proposed that the electrons are embedded in a positive sphere. His proposal was similar to that of a Christmas pudding, where all the electrons in a sphere of positive charge were just like how dry fruits are there in a spherical pudding or a Christmas cake. Then Rutherford, he proposed another atomic model where he did an alpha particle scattering experiment, which led to the discovery of atomic nucleus. And Rutherford's model of atom proposed that every tiny nucleus is present inside an atom, and the electrons, they revolve around the nucleus. But the stability of the atom could not be explained by this model. Finally, Niels Bohr, he proposed a successful model of an atom, and he told that the electrons are distributed in different shells with discrete energy around the nucleus. So if the atomic shells are complete, then the atom will be stable and less reactive. So in this chapter we'll see the rest of the topics. So according to Niels Bohr, the electrons are distributed in different shells. So let's see how the electrons are distributed in different energy orbits or different shells. So the distribution of electrons into different orbits of an atom was suggested by Bohr and Bury. Okay, and the following rules should be followed for writing the number of electrons in the different energy levels or shells. So let's see how we can find the number of electrons in each of the shell. The maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number or energy level index and n is equal to 1, 2, 3. So we already studied in part 1 that the electrons are distributed in different energy levels or shells which have discrete energy, and Bohr explained that these orbits or shells are represented with letters K, L, M, N or numbers 1, 2, 3, 4. Okay, so in order to find the maximum number of electrons in each of this shell, we have the formula 2n square. Okay, so the first orbit or the K shell will be 2 into, here the value of n is 1, so 1 square, which is equal to 2. Hence the maximum number of electrons in K shell is 2. Now the second orbit, n is 2, therefore we will get 2 into 2 square, which is equal to 8. So the maximum number of electrons in the second shell or L shell is 8. Similarly, third orbit or the M shell will be 2 into 3 square, which is equal to 2 into 9 equal to 18. So the number of electrons in the third shell or M shell will be 18. Fourth orbit would be 32. So in this way we could understand the distribution of electrons in each of these orbits. So the first rule was that the distribution of electron in any orbit can be determined by the formula 2n square. And the second rule is that the maximum number of electrons that can be accommodated in the outermost orbit is 8. Say for example argon. See, the maximum electron is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the outermost shell can't hold more than 8 electrons. Third rule is that the electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. That is, the electrons first occupy the lower shell, then it goes like L, K, L, M, N, like that. So here we can see first the K shell is filled, then the L shell is filled, then it goes to M shell. So the shells are filled in a stepwise manner. So this is the atomic structure of the first 18 elements. For hydrogen, the electrons is 1. It accommodates in the K shell. In the case of helium, it is 2 electrons are there. So the distribution of electron in helium would be like this. In the case of lithium, it has 3 electrons. So first the K shell is filled and then the L shell is fixed. Okay. Similarly, each of this shell, after the K shell and the L shell is filled, it goes to the M shell. So this is how the distribution of electron in an orbit takes place. Now this outermost orbit of an atom is termed as valence shell. Okay, so let's understand more about valence shell, valence electrons and valency. So we have learned how the electrons in an atom are arranged in different shells or orbit. Now the outermost orbit of an atom are called as valence shells, and the electrons present in the outermost shell of an atom are known as valence electrons. The electrons present in the outermost shell of an atom are called as valence electron. Now from the bohr-bury scheme, the outermost shell of an atom can accommodate only a maximum of 8 electrons. That is, the outermost shell can't hold more than 8 electrons. This means that the combining capacity or the valency of that atom would be 0. Now what was this combining capacity? We have already studied in the previous chapter. Combining capacity of an atom is the ability to bond with each other elements, like to make molecules and all. So if the outermost shell is filled with 8 electrons or a maximum of 8 electrons, it means that the combining capacity or the valency is 0. And it is also observed that all those atoms which is completely filled with 8 electrons in the outermost shell, it showed a certain chemical activity or certain chemical reaction, as these electrons would have much more energy as compared to the electrons inside the inner shells. Okay. Now of the inert elements, you know what are inert elements? The elements that belong to the group called as noble gases are called as inert elements, like argon, helium, neon, krypton, etc. So out of these inert elements, helium has 2 electrons in the outermost shell. Okay, so the valency here is also 0. But all the rest of the inert elements, they have 8 electrons in the outermost shells. Hence the valency or the combining capacity is 0. So the combining capacity is the tendency to react and form molecules with atoms of the same or different elements. Okay, thus we can explain combining capacity as an attempt to attain a fully filled outermost shell. This fully filled outermost shell or the outermost shell, which have 8 electrons, is said to possess an octet, and atoms would thus react to achieve an octet in the outermost shell. That is, every element, it has an urge to have this 8 electrons in the outermost shell. Hence, in order to achieve this 8 electrons, the atoms would either gain or lose or share electrons. Say for example, here the sodium, it consists of only 1 electron in the outermost shell. Okay, so it actually donates this electron. Okay, hence this becomes a sodium cation. In the case of chlorine, in order to attain its octet, it requires 1 more electron, right? So what it will do, it will gain from 1 electron from this sodium. So here the sodium and chlorine, they combine by exchanging electrons to form sodium chloride. Okay, so the number of electrons gained or lost or shared so as to make an octet of an electrons in the outermost shell gives us directly the combining capacity of the element or the valency. So understood, right? What is valency and combining capacity? If you have doubts, message me in the comment section. Okay. Now let's take some other examples. Let's take the case of hydrogen, lithium, sodium. These all contains 1 electron in the outermost shell. Therefore, each one of them can lose one electron. Okay, hence the valency is 1. Now let's take the case of magnesium and aluminium. In the case of magnesium, it has 2 electrons in the outermost shell, hence the valency is 2. And the case of aluminium, it has 3 electrons in the outermost shell. Here also the valency is 3. Okay, so here also these atoms, they lose electrons, right? But in some cases, if the number of electrons in the outermost shell of an atom is close to its full capacity, then the valency is determined in a different way. Say for example, fluorine atom. Here it has 7 electrons. So the valency could be 7. But it is easier for fluorine to gain 1 electron instead of losing electrons, right? Losing 7 electrons. Hence the valency is determined by subtracting 7 electrons from the octet, and this gives you a valency of 1 for fluorine. So the valency of fluorine would be 1. Therefore, an atom of each element has a definite combining capacity called as valency. Okay. Now the composition of atoms of first 18 elements with the distribution of electrons in each shell is provided here. Let's take the case of helium. Helium, it has 2 electrons. So first it's distributed in the K shell. Okay, so the shell is filled, hence the valency is 0. Okay, now let's take the case of carbon. It has 6 is the atomic number. It has electrons 6, and it's distributed first in the K shell. K has 2 electrons. Then after the K shell is filled, it moves on to the next cell, which is L. It has 4 electrons. Okay, so the valency would be 4. Now let's take the case of oxygen. In the oxygen, the atomic number is 8. Number of electrons would be 8 because the number of protons and the number of electrons are the same, right? Because the atoms are neutral. Okay, so first we'll fill the K shell with 2, then L shell is filled with 6. Okay, now in this case, if you notice that the number of electrons in the outermost shell is close to octet. So how will we find the valency? Just in the previous slide we saw how we obtained the valency from fluorine, right? We subtract 8 with this number of electrons. 8 minus 6, which is equal to 2. So the valency is 2. Let's take the example of sulfur also. Here also the valency or the outermost shell have 6 electrons. Okay, so 8 minus 6, which is equal to 2. In the case of argon, it is fully filled, hence the valency is 0. So in this, like this, we are able to understand the distribution of electrons in various shells. Now let's study about atomic number and mass number. So we have already learned that protons are present in the nucleus of an atom. Okay, so it is this number of protons of an atom which determines the atomic number. It is denoted by Z. All the atoms of an element have the same atomic number Z. Say for example, hydrogen. Z is equal to 1 because in hydrogen only 1 proton is present in the nucleus. Similarly for carbon, it has 6 protons. Therefore the atomic number of carbon is 6. In the case of nitrogen, the atomic number is 7. Oxygen, it is 8. Okay, so all the elements are defined by the number of protons they possess. Therefore, atomic number is defined as the total number of protons present in the nucleus of an atom. Atomic number is defined as the total number of protons present in the nucleus of an atom. Let's see what is mass number. So we have already studied that the mass of an atom is practically due to the protons and neutrons alone, okay, which are present in the nucleus of an atom. Hence the protons and neutrons are called as nucleons, and the mass of an atom resides inside the nucleus. We already saw in part 1, right, how J.J. Chadwick found about this neutrons. Okay, so the mass of an atom resides inside the nucleus. Say for example, the mass of carbon is 12U. Why? Because it consists of 6 protons and 6 neutrons. Okay, 6U plus 6U is equal to 12U. The mass of aluminium is 27U. Why is that? Because it consists of 13 protons and 14 neutrons. Okay, so the mass is equal to 13 plus 14, which is equal to 27U. Therefore, the mass of an atom is mainly due to the protons and neutrons. Thus, we can define mass number as the sum of total number of protons and neutrons present in the nucleus of an atom. Mass number is defined as the sum of total number of protons and neutrons present in the nucleus of an atom. It is denoted by A. In the notation for an atom, hence we can express this atomic number and mass number and the symbol of an element like this. Symbol of an element, mass number on the top, atomic number on the bottom. So the symbolic representation would be like this. X is the symbol of an element, mass number is A, atomic number is Z. See here in the carbon, the symbol of an element, atomic number, mass number. Now let's see about isotopes. So in nature, a number of atoms of some elements have the same atomic number but different mass number. For example, in the case of hydrogen atom, it has 3 atomic species, namely protium, deuterium and tritium. See here we can see it has the same atomic number but the mass numbers are different. See 1, 2 and 3. Similarly, carbon atom, it also have 3 species. In the case of chlorine, here also see it has the different mass numbers but the same atomic number. Okay, so isotopes are defined as the atoms of the same element having the same atomic number but different mass numbers. Therefore, 3 isotopes of hydrogen atom are protium, deuterium and tritium. Okay. So many elements consist of a mixture of isotopes. Okay, say for example lithium, it has 3 isotopic forms. See, so each isotope of an element is a pure substance. The chemical properties of these isotopes are similar, but their physical properties are different. Now let's take example of chlorine. Chlorine occurs in the nature in 2 isotopic forms with masses of 35U and 37U in the ratio 3:1. So how will we calculate the mass of chlorine atom then? We'll take the average mass. Okay, so it is given that the isotopic masses form with masses 35U and 37U are in the ratio of 3:1. So if we convert it into percentage, it would be 75% and 25%. So in order to calculate the average mass, we'll give 35 into 75 by 100 plus 37 into 25 by 100, which is equal to 105 by 4 plus 37 by 4, which is equal to 142 by 4. Thus the mass of chlorine atom would be 35.5. So from all this we can say that the mass of an atom of any natural element is taken as the average mass of all the atoms of that element. If an element has no isotopes, then the mass of an atom would be same as the number of protons and neutrons in it, right? We have already studied how to calculate the mass of an atom. So if it has no isotopes, the mass of the atom would be same as the number of protons and neutrons. But if an element occurs in isotopic forms, then how will we calculate the mass? We'll take the average mass, just like how we did for chlorine. So now let's see the applications of isotopes. So some isotopes have special properties in which find them useful in various fields. For example, the isotope of uranium, it is used as a fuel in nuclear reactors. An isotope of cobalt, it is used in the treatment of cancer. An isotope of iodine, it is used in the treatment of goiter. So these all are the applications of isotopes. Now let's see what are isobars. So in order to understand isobars, let's consider some of the elements like calcium, potassium and argon. And if you notice this, we can see that all the atomic number or the number of protons in each of these elements are different. In calcium it is 20, for potassium it is 19, for argon it is 18. But the mass number of all these elements is 40. That is, the total number of nucleons is same in these elements. What are nucleons? The number of protons plus the number of neutrons is called as nucleons. So atoms of different elements with a different atomic number which have the same mass number are known as isobars. Atoms of different elements with the different atomic numbers but the same mass number are called as isobars. So that's all for chapter 4, structure of an atom. Tune in soon for the next session. Till then, stay safe, take care, may God bless you all. Thank you and bye-bye.